Hi folks, and welcome to your first little video lesson that we're going to try and work through together here. As I mentioned, we are skipping over Unit 3 and jumping straight to Unit 4, which is going to start us off talking about one of two units that's going to all revolve around triangles. Specifically, we're going to start today talking about similar triangles. So first off, similar triangles means two triangles that have the same shape but different sizes. That's the key. So if we take a look at the little note page that I've created for you here, you can see these two triangles are the exact kind of example that we're talking about. You can see that they clearly have the same shape to them, but they have different sizes. One is bigger than the other. So then we need to look at what are the rules that make that happen? What types of things occur when these triangles are similar? Well, we can see another rule that I've mentioned here. So two triangles are similar if for any angle in the smaller triangle, I can match it up with an equally sized angle in the larger triangle. So what does that mean? Well, let's use a little bit of color and we'll move back down to our two triangles here to take a look. So this says that if I take an angle in one of our triangles, let's say angle A in here, that's from the smaller triangle. Our rule says that if these triangles are similar, there should be an equally sized angle that matches up with it in the bigger triangle. So you might be able to see what that is. That's angle D over here. So those two ones that I've labeled with orange, those are the same angle size, and that's what creates the same shape in that corner. We can do that for other angles too. Let's use a different color. So what about if I'm talking about angle B here? Well, you can probably see that that's going to match up with angle E in our larger triangle here as well. And just to verify, let's take our third angle in the small triangle, which we'll call C. We can see that it has a matching one that it's equal to in F. So as long as we have these three pairs of matching angles that are equal, we know that we have similar triangles. So from there, it's important to note a few things that can help us actually find unknown lengths. So you can see, for example, in triangle DEF, we know one of the sides is 9 units long, but the other two are just labeled as X and Y. We don't actually know how long those sides are yet. So we want to use things that we know about similar triangles to come up with a way to figure out what those are. And here's the key that we're going to use. It's this other statement that you'll now see at the top of my screen that says, when we take the length of a side in the smaller triangle and we divide it by the length of the corresponding, or in other words, the matching side in the larger triangle, we'll get only one specific number. And that same number is going to come up no matter which side we start with. And then we're going to try and use this fact to help us find the unknown pieces inside of triangles. So, for example, if I look at these two triangles here, I can see that I have one side here that's labeled with a 3, and it has a matching or a corresponding side over here with the 9. I can see that this 4 has a matching or a corresponding side with this Y, and I can also see that this 6 has a matching or a corresponding side with this X. So every side and every length of every side in the smaller triangle has one that it matches up with in the bigger triangle. And that word matching, we sometimes replace with the word corresponds to. So it corresponds to the side length of the other triangle. And what we can do now is do some division. So what our statement is generally saying is that if we take two sides that match up and we divide them by each other. So for example, I'm going to take 3 from the smaller triangle and divide it by 9 in the larger triangle. Well, what we know is that whatever number we get when we divide those out, and if you did that on your calculator, you'd see that that's like 0.33333 and so on. But it's not so much important what that number is, but what's important to note is that whatever I get when I calculate that is going to be the same, or in other words, equal to what I would get if I divided some other side by its matching or corresponding side. So for example, if I take 4, the side that's 4 units long from the small triangle, that's the one that's BC, Well, that matches up with the side EF, or in other words, the one that's labeled with a Y. So I don't actually know what Y is, but I know that whatever I get when I do 4 divided by Y has to be equal to or the same as whatever I got when I did 4 or 3 divided by 9. So these two things must be equal to each other. And that means I have this statement with only one unknown piece in it that I can try and solve for. But that's not the only thing we can say. We could also say that all of this is still equal to a third pair of matching sides. So I also have a side, you can call it AC if you want. It's got 6 units long, and it matches up with side X in the larger triangle. If I just show you there, that's X in the larger triangle. So now, suddenly I have something that connects all of these sides together. But now we've got a bit of a weird looking statement where we've got these 3 fractions that all seem to be equal to each other. And not only that, it means there's an X and a Y that we don't know. So that's too much information to all put together all at once and to try and solve for all at once. So instead what we do is we focus in on just 2 of the fractions at a time. So the key is first to identify one complete fraction that you know. So I'm circling that first one because I know both the top number and the bottom number in that fraction. But of course, the other 2 fractions have something missing. Specifically, the bottom number is missing in each one. So what I do is I take the one that I know completely, and I first match it up with one of the other fractions that's missing something. So for now, I'm actually going to ignore the 6 over x part. I'm going to ignore that one completely and just pull all of this information out into a little separate statement below. And I'll just use a different color for that. So I can say 3 over 9 is equal to 4 over y. And eventually later we'll try and figure out what x is equal to, but for now, let's just focus on using this statement to solve for y. Well, the easiest way to go about something like this is using a method called cross-multiplying. And cross-multiplying says that when I multiply the numbers in these 2 fractions in a crisscross pattern, like so, the 2 results that I get will be equal to each other. So when I do 3 times y, well, for now, I'm just going to call that 3y. On the other side, when I do 9 times 4, I get 36. So now that crisscross multiplication method has given me 3y is equal to 36. But really, I want to know what just y is all by itself. So what I'm going to do is I'm going to take the 3y and divide it by 3 and balance the equation by dividing by 3 on the other side. So we're still just using our equation solving skills that we learned before. Of course, these reduce down to 1, so we don't have to write them anymore. And we find that the y value we were looking for is actually just 12. So we've solved for the unknown length of that side, y. But we still don't know what x is equal to. So let's take a moment to figure that out. Now I'm going to reuse the one that I already had, 3 over 9. I'm going to reuse that fraction, and I'm going to start with that one again. But now I'm going to make it equal to 6 over x, make it equal to a different ratio that I know it's also equal to. And then once again, I'm going to cross multiply, and I'll use a different color just to emphasize my crisscrosses. So I'll do 3 times x on one side, and I'm going to make that equal to 9 times 6 on the other side. So 3 times x is equal to 3x. 9 times 6 is equal to 54. So if I divide both sides by 3, give myself a little bit of room underneath, these are going to reduce to 1s, x is going to be equal to 18 because 54 divided by 3 is 18. So that process that started with all of this information actually broke down into two separate calculations where we were able to separately calculate x and y. But notice that we used 3/9 in both cases because you want to make use of any full ratio that you know, any complete fraction that you already have. Now, I admit that when we're trying to solve for two different pieces of unknown information, like we just were, an x and a y, that can get a little bit confusing. So let's do a couple more simpler examples just so you can really see how repetitive this process becomes when you get a lot of practice with it. And in general, if, as I've said all along, if you don't have a printed version of this, you can just jot down or copy down this example along with me. And you can always pause the video at any time to take your time to sketch out these diagrams if you need to, and then just work along with me. So first off, we need to identify matching sides. Well, we can see that this 18 side matches up with this 9 side. We can also see that this 20 clearly seems to match up with this x. So there's our matching or our corresponding sides. And now we're going to take those corresponding sides and put them together into ratios. Now, here's the interesting thing. We don't have to start with the smaller triangle and put that on top. We could start with the bigger triangle if we want, as long as we stay consistent. So here I'm going to put the bigger triangle's number on top. I'm going to put the 18 on top and divide it by its corresponding side, divide it by 9. And then I can make that equal to a similar division of some other pair of sides. So I have another side of the big triangle, that's a 20, and I can divide it by the side that it matches up with. As soon as I have this statement, I can go to work using my cross multiplication. So now I'm going to say that I can do 18 times x, and whatever I get will be equal to 20 times 9. So I'll give myself a little bit more room here. Well, 18 times x, for now, we'll just call that 18x. And we know that that's equal to whatever we get when we multiply 20 times 9, or 20 times 9. So 20 times 9 is just 180. And then to get the x all by itself, we need to divide it by 18 on the left, and we balance that out by dividing by 18 on the right. Those become 1s, and x is just equal to whatever we get on the right side, which is 10. So x, that x value that we don't know in this case, must just be equal to 10. Let's try one more example as well. This example B looks very similar to the previous one, doesn't look a whole lot more challenging, but one thing we need to be careful of is that these triangles, even though they are the same shape, are not oriented or turning the same way. One's pointed in a different direction from the other. So we need to imagine that we take this triangle and take this edge of it and rotate it, oopsie, and rotate it around so that it is now facing towards the top. So if that edge was rotated so that it was on the top, suddenly what we realize is that this 35 would actually match up with this side that's 5 when we rotate it, because suddenly that 5 side would become the bottom when this whole triangle gets rotated. And that means this 49 actually must match up with this x, because again, when the smaller triangle gets rotated, the x will be on the left side of the triangle, just like the 49 would. So now we know which ones match up, and now we're going to try and use that to build our ratios. Well, always start with a complete one that you know. So for example, I know that the big triangle has a side that's 35, and more importantly, I know that the side that matches up with it in the other triangle is 5. So I put those together in a fraction. The other one has one side that's 49, but then a smaller side that I don't know that it matches up with. So that's my x. After doing a lot of practice in these, you should be getting very comfortable at cross multiplication, but the first few times you do it, it's okay to really take your time. 35 times x is just 35x. 5 times 49, you can use a calculator if you have to, is 245. I divide this side by 35 as usual. That reduces these down to ones that I don't have to write anymore. And dividing this side by 35 is again where the calculator might help you out a little bit, but it actually works out nicely. It's exactly 7. So our unknown x value in this case is 7. So if we just step back for a second and review that overall process, we need to set up a statement that has one fraction equal to another fraction. And we'll always have one unknown piece in one of those fractions. But the other fraction should be complete. In other words, we know both pieces. So in the first example, the 18 over 9 was our complete fraction that we knew, and we knew that that was equal to 20 over x that had a missing piece to it. As long as we can set up a statement like that, we use cross multiplication to finish it off. Try as much practice as you can, and make sure you're emailing me or contacting me however you can if you feel like you need some extra help.